Okay, this video is going to go over questions from the Chapter 6 packet, starting with number 5. So number 5 is a question on your list, and if you look at that slope field, you can see, that the slopes here, you can kind of see, I'm using a highlighter so it's thicker, but you can see, the direction that these are going. These are all heading that way. So what I know about the actual graph of the solution is that, looking at E, that's not going to work because the slopes are not decreasing, they're increasing for negative values. I know it's also not D, so I can eliminate those. I can eliminate C because this function's increasing, so the slopes would have to be positive, and they are not. So now I'm in between A and B. And both of them, I'm not really sure which one's going to work, but I can tell that this would have a horizontal tangent. So I know at the point 1, comma, maybe 1.5, the slope would have to be 0, and it's not. Okay, so I can just try to figure out based on those values. So the answer for number 5 was B. And then number 21 was the next one on that set. And this one, yeah, the way they wrote it was a little weird. They're basically saying, if your values are above the x-axis, if they're greater than 0, would the limit as x approaches infinity go to 0? Well, the limit as x approaches infinity, those values are soaring. Those slopes are getting steeper, so that's false. Then they're saying between -2 and 0, okay, the y values of -2 and 0, is the limit as x approaches infinity about -2, and for values that are less than -2, will the limit values as x approaches 0 be -2? And they do appear that there is going to be like a horizontal asymptote since those slopes are 0. So those two statements would both be true, which meant that it was D. Okay, I'm now going to go to pages 15 to 17 that were in the Chapter 6 packet and go over a couple of questions there. So I had a question on number 3. So this one, they gave you some added information you didn't need. It was the rate of change of the atmospheric pressure with respect to the altitude. So we want to know what variables we're talking about. So the rate of change of the pressure, dP dt, is proportional to, so equals K times P. So we know that that is the differential equation that's always going to give us the solution P equals CE to the KT. And then it says at sea level, so altitude is 0. So at 0, the pressure is 101.3, so I've found my C value, 101.3, using the point 0, comma, 101.3. Then I'm going to use the second point. When the height is 1,000, then, or when the altitude's 1,000, then the pressure is 87.1. Okay, so I put in 87.1 for P. I'm putting in 1,000 for the T, which would be the altitude. I have to divide both sides by 101.3, and then I can ln both sides, because ln times e to the 1,000k will just give you that exponent of 1,000k. And then k is going to be this number that I definitely want to store in my calculator because we don't want to round it. So to figure out part B, if the altitude is 6,187 meters, I want to put 6187 in for my T, but I want to leave that K value. So whether you stored that in A or you're plugging it in, ln 87.1 over 101.3, all divided by 1,000, but you have to keep it constant, okay? And then for part C, they want to know, well, when or at what altitude would the pressure be 50? So now P is 50. So I'm going to solve and find out this A, I called it A value. So I divided both sides by 101.3, then ln both sides, because ln of E will just give me the exponent. Now I used A because A was, that stored number, and I divided by that number, which was already stored on my calculator, to get the answer in meters. Okay, 4B was another question. Once you get the actual general solution. C equals 0.00372 e to the kt. I'm going to use where it says on the second visit, the measure was 0.00219. That second visit was 8 hours later. Okay, so 0.00372 was the initial value at time 0. 8 hours later, it was 0.00219. So I know my C value, and then I know 0.00219 is that C value when time is 8. I'm going to divide both sides by 0.00372, ln both sides, and then divide by 8. I'm going to store that value. So my function is C equals 0.00372 e to that stored value in A times T. Part C says, the doctor says you might have serious body damage if the poison concentration has ever been as high as 0.015. So we're going to put 0.015 in for that concentration, divide both sides by 0.00372, ln both sides, and then divide by that stored number to get your time, which tells us that that concentration would have never been that high. Okay, and the last question was number 6. So number 6, the gentleman that invented logarithms was the first person to answer this question. If money compounds at a rate proportional to the amount you now have, and you invest at 5%. Well, if you invest for 5%, it doesn't matter what initial amount you put in. I could put in 1.05 equals 1C. 1.05 C equals 1C e to the kt. When I divide both sides, doesn't matter what that initial C is, you'll get 1.05. So if you use $1, you can use $1.05. If you use 100, you use 105. So regardless of what you use, this is going to be 1.05. ln both sides to find out K, get your general equation. Now, how long will it take $100 to grow to 1,000? So I'm going to put 1,000 into the left side, 100 into the initial, and then I'm going to solve it. Then it wants to know how long will it take any amount to triple. It doesn't matter what your initial amount is. If you have 3C equals C, when you divide by C, you'll get 3. If it were doubled, it would always be 2. So then I can ln both sides, divide by ln of 1.05 to get my answer. And then if you invest $1,000, so there's your initial, will you be a millionaire? So we want to see if you have $1 million. So if you divide both sides by 1,000, ln both sides, you'll get 141.581, and you could figure out that that's in years, so the answer would probably be no. Okay, so I think I got all of the questions from pages 15 to 17. So I